My name is Herwig Baumgartner. I'm the Applied Studies Coordinator here at SCIARC. And we have a really great guest here today. The first time I remember I met Bill Zahner was actually in the mid-90s while working on the Experience Music project for Frank Gehry. And I remember when they were hired to do the metal skin, I thought to myself, how are they going to build this crazy metal skin? And it's still, I think, we just talked about this, one of the most complex envelopes I've ever worked on, and still very impressive. Bill Zahner and his company have been around for a long time and have worked pretty much with every major architect that you can think of. Here in town, they've worked on the Amazon project with Morphosis and on the Peterson Museum, amongst other things. I think the amazing thing about Bill and his company is they really have pushed construction, the digital, and fabrication to a whole nother level in terms of innovation, craftsmanship, and dedication to design. He is a true collaborator to many architects and often has to juggle a very difficult thing between a high-level design and budgetary constraints and buildability, etc. When I initially approached Bill to teach a masterclass here at SCIARC, he replied right back and was super excited about it and came up with an idea of how students can actually work on a real project, design it, he will build it. And that's, I think that's what we're kicking off today. After this lecture, Bill's going to start with a workshop, and then students will be going to his factory, Kansas City, in about a month or so, and do a 2-day workshop there, which should be fantastic. See all the great work you guys do, lots of markups, materials. And then we're going to wrap up by Bill coming back in November for final review to review the designs and hopefully then get that built. So without further ado, welcome Bill Zahner to SCIARC.
Thank you. It's always fun to, like I said, it's always fun to come talk to future customers, about the work you do and how we do it with architects. We're known for these wonderful projects, worked with several people here on some of these Frank Gehry projects over the years. And it's the geometry, working on trying to get the forms right and the materials that we're going to use. So what I'm going to show you today is a lot of different aspects of the materials that we use on building some of this and some of the ways we go about doing it. We're a 121-year-old company, started by my great-grandfather in 1897. We engineer, fabricate, and install most of the work we do. We work in different materials, different metals, mainly. Do a little bit in glass, I'll show you in a down a ways here, but we work mainly in the various metals, stainless steel, aluminum, zinc, different finishes of copper and of zinc. This blackened stainless steel piece for Chicago, Bloomingdale's. But we work in the digital world where we work with the artists and architects to create things. We start at the digital aspect. And this particular project's an interesting one to talk to you all as young designers about. It's the Mark Fornes, it's a pavilion that he wanted to build in Columbia, Maryland. The client was all excited about working with this designer and how do we get it done? So we were hired to create everything from the foundations up. And Arup was the engineer involved with the project. And one of the things that we first do is, that one of the requirements or constraints, they wanted to make sure no water got on the people that were inside the structure. So we do some analysis of flow of water across the surface. We want to know how it's not going to be fully enclosed, but we want to be sure that we can shed water off the surface. We do an analysis of the curvature so we can kind of get a feel for how much shaping we got to do to the pieces. So we can make sure that we understand how we're going to put these things together. But one of the constraints that happened on this one was the structure. Mark Fornes, if you see his work, It's all skin and the way the skin works. But this is a rather large piece. The client was a bit concerned, and so hired the engineer to analyze it. And one thing you run into and I'm an engineer, but one thing you run into a lot of times on the engineering aspect is there's nothing for them to really gain by making it simpler. So they end up, in this case, we have a bunch of 10-inch diameter tubes, steel tubes, moment connections, bolted up. The designer Mark Fornes was not really happy. He didn't like all the structure that he had to put in underneath his piece. We ended up building, we also had to build what we call our ZEP frame system, where we make all the undercarriage in the plant, put the panels together, and send it out to the project. And one constraint came back after we were underway was the engineer said, well, you got to distribute that load across those tubes. You can't point load it. So we had to then put anchor points all along every tube. So all these different constraints that come into play that affect, one, the cost of building it, and two, the architecture. In the end, we were able to pull it off and made something that's quite elegant. Everybody's pretty happy about it. It was, I think, a donation from us since we had so much to do on this steel inner structure. And a lot of times you don't see it. In this case, you're gonna be able to see it. But it's a beautiful little pavilion out in Columbia, Maryland. We get a lot of our influence on what we do working with the architects that we work with from the artists. We do a lot of work with artists, and they influence a lot of the way that we approach a project. So in this particular project, this is a giant tobacco leaf. And the artist, good friend of mine, Hendrix, wanted this chandelier constructed in in Mexico City, the Ciutadella, which was an old tobacco factory. So it's a series of tobacco leaves, and each one a little smaller. And the top one's about 5 meters across, and they're cut in half-inch plate aluminum. And we powder coat them. So here you can see up through, we made like a smoke ring going up through it. The support pieces are these stainless steel cables, and we used a little device. So we wanted to make sure that the structure holding them added to his art and didn't take away from the art. We wanted to make sure that they, if you saw them, you would think they were meant to be. So a lot of the times when we're working with the artists in particular, we want the structure to be something that's there, but not so visible. We want it to work with the piece. And that's the real challenge, I think, in today's more intricate geometry, is getting the things to work together. Because actually the economy is pulled out at those points. And then for us, when we work with a different material, this is the same artist, a blackened aluminum, black anodized screen. We want to make sure that the edges and what we produce where the pieces come together is really clean. Because we don't want, back in the days when I started in the late 70s, early 80s, the sheet metal manual had flashings and all these cover points. And the more I looked at those, the more I interpret those as Band-Aids. And I look at how do we make, a joint come out clean. And the art today, a lot of times, is kind of morphing into the architecture. And it's being used and more into architecture. And so like in this project in Aguascalientes, Mexico, we produced these I say the name wrong, the purple flower tree. The artist, these are leaves from that plant. And so we're trying to make the structure disappear, the main structure, but all the intermediate structure kind of blends in with the art. And forms this great little patio for people to enjoy during the day and at night. It becomes the center point for them. And again, we use water jet, and I'll show you in a moment, to cut the pieces. Another thing that we try to do for the architects we work with is control how the joints come together. So much of what we do, in our way that things are constructed, the lines maybe are all straight. Got to have straight, got to have the lines, the pieces are rectangles, so everything needs to be straight. But if it messes with the art, you look at the top part, why not make it disappear? How can we actually, using the technology we have, make the joint line not be a straight line, because the art isn't straight. We can make them come together to work with appearance, and so that joint line disappears. We're challenged by Herzog and Dimron on a project in Prada, a Prada store in Japan. And they wanted all the copper panels to have this texture across them, but they wanted to make sure that, they said, well, we don't want any seams. Don't want any seams, weld it up. I said, how do I ship it to Japan? I said, look, we'll do a seam, but we got to have some seams to make this thing work. And so we worked with our technology and created this, we called it our zipper seam, that worked with the pattern. And when we showed them this, they started they said, well, we want to show that seam. It's kind of neat. So here's the seam running through the piece. Now, one thing that we run into when I do these little pieces, when you get to the larger project and you're doing the seam, here's the curves, and it came out really nicely. But when you do the larger one, you'll see here, I've got some horizontal seams in the larger wall and vertical. What we found was as we were pressing the copper and putting these dimples in and out on the copper sheet, it stretched it slightly, just so slightly, so that when if we start every sheet at the same direction, they're all going to stretch the same and it'll work. But if you start them and you have them intersect you're breaking up a four-way joint, for instance, in this case, you have an intersection piece where one part has been elongated more than the other. So we have to get in and adjust things to kind of predict how the metal is going to move. You can do it another way by changing the temper of the metal. But that's where, hopefully our expertise fits in with the designer's interests, because they want this thing to be very monolithic in appearance. Another thing they said, we want these, they saw we could get by the joint, they want the thing now to go around a curve. And in this case, the geometric pattern going around a curve is a little trickier. So we made this sphere, we put the little bumps in it, and then we welded the piece up. And here it's just tacked together to make the elbow of the piece. And there it's polished out, so it disappears and goes around the corner. So like I said, we do a lot of work with water jet. And water jet, we can cut 6-inch pieces of steel. You can cut glass. You can cut paper or aluminum in this case. So this is 1/2-inch aluminum. You can see the edge is frosted because the water is moving at about 90,000 PSI, 100,000 PSI. We can cut these really delicate shapes and make very intricate forms with a water jet and thick material. Here's a project working with Jan again in Qatar, where we cut these large plates of a design of his. So it's to make it continuous across and get rid of the, kind of also again sort of conceal the structure that holds it in place. These are 11 meters tall, made in 2 sections. Our water jet will cut 3.5 meters, or no, 4.5 meters in length. And so the large panel sections assembled, and you can see the joint here between the panels, and it all kind of moves, expands, and contracts in the heat in Doha. And there was 2 sides of it and glass in the middle, and it created this courtyard that glows, and people can go out and enjoy the courtyard in 120-degree weather. But it's a rather beautiful piece, trying to make it so that it all works together, expands and contracts, so it doesn't bind up, and it almost looks as if it's floating. So we also, this was a challenge with an architect friend for Gensler. He wanted to do a piece of art for the Hyatt Regency, and it was down in Houston. And he wanted a piece that's, we wanted to look like the Buffalo Forge portion of the river. So in this case, I wanted to use something a little different than water jet, because water jet gives that frosted edge. So we used our mill. And the mill, it's like a router, but bigger and does much quicker and thicker pieces of metal. And so I wanted to capture the light reflectivity off that edge. So by milling it, you're taking these little shards off super fast, and you're getting this layering effect. So when we were building it, we take plates of the aluminum and, we cut out areas to make it a little lighter. But that's all layered up, half-inch plates of aluminum. And there's that hollowed out sections to lighten it up. And then we put the river across the wall. And we wanted to use a contrasting material, so we used pre-weathered steel, or weathering steel. It's copper-bearing steel, so we can pre-weather it and get it to this beautiful tone. And that gives this contrasting appearance. But the mill allows us to do some other things, because so much of your architecture has to do with how the eye perceives edges, as well as the surface, but the edges are important to us. And so the mill makes them glow, so that you can get, it takes on a different character. And when we were doing these in aluminum, and mirror polished aluminum, we also then polished over it and almost made it look like silver, very soft cast silver. We mill other materials. This is an artist was doing a project in DC, and we were doing these 1-inch thick plates of bronze. And the idea was to do it was like to make it look like a printing press, like the old Gutenberg presses, a plate. So we milled it out. So here we mill it, and these are the mill lines. And these are letters. It's Latin in reverse. Looking at a mirror, you could read it, I guess. And then we needle hammered the background to give it sort of this texture and take away those mill lines. And then we oxidized it to make it look like ink had been put on it, and then kind of worked that down a little bit. And each panel was about 10 feet long, 1 foot wide, and there were 88 of them. And one panel took about 10 hours on the mill. So it was a lot of shifts. We even had this marginalia, which is the part in it was to be the first page of Genesis on the Bible. And so the marginalia is a part on the side. We mill it out. We had to do some different steps to sequence it to make it work. And here's the panels going up on this Museum of the Bible. Now, the artist is Larry Kirkland. I don't think he'd mind since I'm being recorded. So Larry and I are out there. Our guys are putting this last panel up here. So as architects, one thing, one advice, whenever you're doing anything with words, check it 2 times, maybe 3 times. So I'm standing up there, we're putting that last panel up there, our guys are out there, and the artist says, I think that panel goes over there. And I go, I can't read reverse Latin, Larry, don't even think it. So I went back to the hotel, and I had called my office and said, check what we've made. Larry thinks it's in reverse, and just check it out. And sure, we'd made it exactly the way it said it. Larry calls in a panic. He goes, we got it wrong. So we had to, I go back out there, we pull it all down. The museum's opening in like 3 weeks. Pull it all down, switch them, put them all back up. Some structural, but we got it done, and it looked fine. We were both looking at each other, and I'm going, somebody's going to figure it out. You're going to try and read it. Another one with Legaretta. This also is in Qatar. They did the School of Foreign Services, And they had these coffer pieces. And once they were done, they wanted to change some things. They wanted to bring more light into the space. So working with the artist, Riccardo Regazzoni, he does these beautiful tessellating forms. So the idea was to create these 48 almost like jewels hanging down from the skylight. The blue color is a protective film that we put on it to protect these. We're going to make them out of aluminum again. And one of the aspects is I didn't want to weld the joint because that would really make it look clunky. So we took these plates of about 6 or 7 millimeter thick aluminum, sliced them, and put these extrusions in there, then pinned them, and created this joinery system. Now the problem with that is the joint down here at the bottom of this, they were 40 foot long. The joint down at the bottom carries very little load. The one at the top carries a lot of load. So it carries the whole weight of the piece. So we had to test them. It's always a good idea on things that are kind of tricky to make sure they calculate right. But we want to rip it apart, find out what load it could take. And we tore some of these apart to see, to make sure that we had it right. It's a shear connection at the joints. And here's the layup. Now, the other thing you run into is they're great hanging, but we got to get them in that view, so you can't just raise them up, they'll break. So we create something called a strong back. That's one of my engineers looking it over, seeing how it works as they're raising the piece up. We're doing the tests in our factory. And the other next challenge is how do we get them from Kansas City to Qatar? You know, we have to ship them in a container. So we nest them, we model that up, and we nest them and they fit well. Here they are hanging in the project, and they go up into the skylight, and they bring light down into the space. So, you know, we water jet aluminum things. This is copper alloy that we've chrome plated for an artist, and this is these are 5 meter long sculptural pieces in a gallery that we worked with this artist. He made 10 different versions of these. But they're cut in 3 millimeter copper alloy that we then chrome plated. Now you can see that each one's a little bit different in size. And you can see how accurate these cuts can be. Now, 5 years ago, you couldn't these are laser cut. We have a laser in one of our plants. It's called a fiber laser. And 5-6 years ago, you could not cut this fine with a laser on a copper alloy or aluminum. They just didn't have the power or the wavelength. And the fiber laser today, super fast. If I did that little piece on the water jet, it would take about 8 hours. On the laser, it takes a matter of seconds. So it's very quick, but incredibly accurate piece of equipment. So in architecture, we get to Zaha Hadid's Broad Art Museum. We had the honor working on this beautiful project for, it was stainless steel, 14 gauge plates, welded on the ends, but everything laid out, again, on the computer so we could get the joints and the systems all lined up, and then we manufacture it based on those same models. So every piece, we V-cut it to get a nice sharp corner. Nice sharp edge, and V-cut is where you actually mill out the part of the metal when you form it. And so it's all made from 14 gauge stainless steel and fitted up. And it came out incredibly well for us. And it's angel hair surface, so it reflects light very softly. But I remember the consultant said, you can't weld this stuff, you'll warp it. And all these ends are welded. And it worked out well. This was a project, worked with some of the folks here. And I show this one because to stainless steel folks that we work with, because this has been up 12 years, 15 years. It's the Weatherhead School, and this picture was taken about a year ago, or the film was, and it looks fantastic. Down low, it's got some corrosion from the de-icing salts they've gotten on them. They need to clean it. We're out there actually working on a little bit of it. But the luster and the architecture looks stunning. And these are made from stamped shingles of stainless steel that interlock. And the scary part too is now that you guys are coming out as architects, you can inspect our work even if it's way up there. You know, it used to be we'd hide everything up there, but now you can go look at it. This was a project working with the artist or architect Randall Stout, late Randall Stout, good friend. We sat on the side and he said, look, I want some metal that kind of emulates the cliffs here. And so we worked with zinc, and the main body of it is zinc that we over-oxidized. We created a zinc hydroxide in the surface, gave it this kind of marbling effect. But we had some interior pieces that were really complex, so we'll create them in the solid model. We end up doing all of this structure ourselves out of aluminum. And so we define everything before it goes to the shop floor. We call it ZEP. We call it, you know, it's simply put, it's getting everything digitally dimensioned before it's fabricated. So the end result is what you all intended it to be. Another one with Howard Elkus, late Howard Elkus, he wanted a design of a woman's scarf over a box for the Neiman Marcus up in Natick Mall. And we did this as well, where we lay out the panels, you know, and how we're going to support them, how they're going to anchor back to the building. So we can predict all this, so it helps us determine how much this is going to cost. This is one of the tools that we might use to, one, tell our people how we're going to install it, but help us get more predictive on how we're going to install it and what we need the structure to be. So we analyze that curved surface and we look at different things that affect our cost. And we work with Elkus Manfredi to find out, you know, ways that we can adjust it slightly, and that equates to cost. So Gaussian's a simple way of determining where the curvature might exceed what we might do with a piece of equipment, and we may have to use something different that's more expensive. So if we can take some of it out and it doesn't affect the geometry or the architectural appearance, you know, we work with them on achieving that. The end result here, and we pre-clad all the panels, shipped them from Kansas City. The end result is this several layers of colored stainless steel that create what looks sort of like a woman's scarf draped over a box. This was the other thing that I think I try and put to our people that work in the plant. You know, when we work for designers, you know, you want it to be, when you have the lines and the edges, you want them to be where you show them. So the thing I try and stress is we want the quality of the edge to be as perfect as we can get it. You know, we don't want it to take away from your design. So we want the edges to come out. No matter if the material is stainless steel, it has to come out as you've indicated it. This is the Meyer Fletcher house by Daniel Liebeskind. A beautiful little home. Another one for Grace Farms. Here we used aluminum, anodized aluminum, but relatively thin sheet. They wanted a very flat surface, but they wanted a profile, a real tight, thin profile. And we were able to make these shed water, but also get rid of any flashings or trim or standing seams. It's what we call sort of a modified inverted seam. Takes water and we control where it's going to go. And there's no, for me, there's no reason to accept anything less than the edges, the fine edge that that should be able to be produced. So now I'll get one closer to home here. This is Peterson Automotive, actually a heck of a lot of fun project to work on, like EMP, a little less nerve-wracking, but a lot of fun. Here's the artist's, or the architect's rendering in Rhino on the far right, then our model as we start adding all the stuff in it in the finished project. So we begin with a Rhino model and we convert it. And we start adding in everything that we're going to put, every piercing, everything we're going to do on it. And in this case, and these are the outer skins, we want to know how everything's going to fit up on the computer. And we used a pipe as our main structure. And a pipe has some, well, first of all, to be able to get the curves, it's one of the better things to use. We used a tube, actually. In this case, we add then these moment connections. So everything's a moment connection. So it's all got to move within itself. And then the thing that's beautiful about a pipe is all of our connections are consistent. The pieces and parts aren't, but the connections are. So that we engineer one type of connection, one type of intersection between the frames and the main structure. And so the computer set up the algorithm right, just predicts out how all these are going to go because it's matching your surface. And we can predict, we're getting better at predicting the skins so that we can pre-make the skins on a slightly curved surface. So the other thing we use it for, and I was showing this to a shipping guy, because these things are so crazy, the shapes are, the cost of transporting them around the world is pretty high. Even from Kansas City to Los Angeles, when you have 100 different truckloads is very, very high, but also logistics of how they arrive. So we lay them all out on in the computer, and they're all sequenced. So every truck, every piece, we know which truck it's on, when it's leaving. So the logistic aspect of it is really important too. It has to arrive at the time. We're doing the same thing. We're doing Google's headquarters. Every container is all laid out. And we're able, by doing the exercise and running it through the algorithm, doing the proof, I think on Google we pulled 50 trucks out. And 50 trucks equates to all that energy, all that cost of 50 trucks. And here they are, we're waiting. We built the whole project in Kansas City before it was ready for us in the field. So we're actually marshaling them from the field. Here's in our plant as they're going together. And this is a day in the plant. And our guys are pretty fast. But we use a Kanban system, so everything kind of arrives in a Kanban for these particular panel systems. And then we let them take a break for lunch here in a minute. There, go eat lunch. But it's almost an orchestration when you see it working right. Every single one's different, but they had certain things that were the same. And one of the parts that were important to us even was this device, which held them during the fabrication, but also allowed us to ship them. It held them on the trucks. So here's the piece, here's the building going together. And you can see we left off every one of these points, and that's a pretty important thing too for these large-scale projects, earthquake area. I want them inspected. We want to inspect every connection before we go, we want them independently inspected to make sure everything's set right. And then we have the skin go over it and seal it up. Even the support pieces were made like a manifold of a car to support the various pieces. But really a lot of fun, and came out very nice. Hopefully I'll get a chance to see it while I'm here, but it's the owner was fantastic to work with. There's the piece. I don't know, does it look this good in person? I haven't seen it. Here's another one. This was in copper, working with Elza Jones and a artist out of Ramona, I'll mess up her last name, out of Santa Fe. This is in the Smithsonian Indian Museum. She wanted to look like a woven basket. So one of the challenges, we're applying patinas on the surface of the copper in one of our buildings. And the trick with that is some of the patina shows up fairly fast, some of it doesn't show up for 24 hours. So you're kind of creating this invisible ink. And here's the finished product. The inside brighter than the outside. We even incorporated things to make it look like it was, one of the challenges, she said, I wanted to look like it's been buried and just dug up after 1,000 years. And there's the piece installed. Now Jeannie Gang's redoing the museum, and I think she's taking it out. And I'm trying to hope that she lets me have it. One of the more fun pieces. But in both plants, mainly in our Texas facility, we do a lot of patinas, both in copper, zinc, and then weathering steel. Do a lot of weathering steel. Now, one of the challenges, obviously, in weathering steel is how to make it quit rusting, how to keep it so that we can go through the cycling. And there's a lot of things we work on today where we're trying to develop surfaces that shed water. Now the one problem with this one is this kind of whitish haze. But in general, you know, we've experimented with different nano coatings, different things that are out in different levels of the marketplace to come up with ways of keeping the material from bleeding on the surface. Now our process in Texas runs it through several cycles, wet and dry cycles, so it takes it, we're trying to get it to what's called ferric hydroxide, because it's insoluble and it's really stiff. This one had it inside and outside of the building, the staircases, so you didn't want anybody to rub against it and it'd come off on them. This is a zinc. This is actually what we call Rhino zinc, and we punch a lot of holes, and we call it image wall. There's actually an image you can kind of see in that image, that particular view. But it's an oxidized zinc where we're building an oxide over the surface. We get into, I had to pull off a slide because we were being recorded, but we get into a lot of restoration of art. Hopefully, I'm trying to think by the time you're all come whether I'm going to have a piece there, but I've done about 40 some odd Donald Judd pieces, and he's, you know, for minimalist artist, his work is fantastic. But one of the things he got into doing in the early 70s was using anodized aluminum, di-anodized aluminum. You don't see it as often except in some small things today, but the di-anodizing was a newer concept back in the 50s. So we've gotten into a lot of investigating on the dyeing of aluminum, the dyeing of the anodized. So this particular one, I was involved with the restoration of the anodized coating. And it had been done, and it has started to fade. You can't really see the fade in that picture. But we analyzed the surface. We want to know what the base metal, so this is very close up, looking at we measure the depth of the anodized that was done on them, because if we're restoring a piece of art, we really can't can't adjust that surface. But Donald Judd, when he worked on this particular one, he initially had it, the information was that it was gold. It was a golden color. He didn't like it, and he had it re-anodized green. And you can kind of see Now, in this one, you can see the fade. So those bullnose pieces are here, so you can see how much it's faded in the green. So I had to match the original dye that was used back in 1971. And that was where these cups came across. I was reading something and trying to do a little research on what was out there then, and I found this Hellerware. Your great-grandmothers or grandmothers probably had these out, and it was this green anodized done in Italy, where we suspected this had been done. And I found this, I ordered it on eBay, and it matched exactly. So we were able to come up with the dye number. We ran several tests. And in anodizing, what happens is you dip it in various tanks. And one of the tanks is the one with all that fuzzy stuff on it. That's sodium hydroxide, caustic soda. So it dissolves aluminum oxide. So we're going to dip this Judd piece and take the color off of it and then put it back on. Which is here, the color's off the bullnose pieces. And one of the things that happened is the bullnose forms are made out of solids, and they anodize differently than the original base, and they faded quicker because it wasn't very thick. Here's the finished piece, and we were able to match it, get the finish down just right. And I was able to uncover when I took the piece apart that it had been golden at one time underneath some of the nuts. But coloring, putting the dyes in like that black, I think it's something that's going to be more and more improved for your use in the future, particularly interiors. But there's a company in, I think it's Switzerland, that Clariant dyes, that they still are producing the original dyes, but they've made them better. So working with artists, one of the things, and architects, is the way the light, again, reflects off the surfaces. This artist is Ewert Higelman. And we take and we implode these boxes. He's actually going to have a show in, he's out of, Ewert's out of Amsterdam. He's going to have a show down at MoMA. He's 80 years old, and we make these beautiful stainless steel boxes and then suck the air out of them and they collapse. And there's this is in my office one, but we've done a whole slug of these different ones. But so getting the way the light reflects this particular home, the owner wanted it to look like a curtain. So these are stainless steel panels with a different finish that kind of gives that soft curtainy appearance to it. Using our mill, we've been experimenting, working with an architect for Christian Dior on a Christian Dior project, trying to figure out, okay, how do we mill into the plate effectively to create very custom surfaces for designers. So this one's it's out of a 5/8" plate, but it's very deep milled. So we started looking at other ways of doing this, modifying how fast the mill goes, what mill tool we used, again, to give that information to you all to design with, if it's of interest. And the thing this doesn't capture is the way the light reflects off this sort of fractured surface. Another way we've done it is where we've taken stainless steel cloth, shaped it, and then coated it in zinc. This one, Foster was working on the Virgin Galactic, and he said they wanted surfaces that looked like they came from another planet for some of the interiors. So here we took nickel silver and took it up to about 4,000 degrees and melted the surface and created it and hit it with air, and you got these incredible shapes. We've done it on some very large copper alloy panels, because what happens, it starts unalloying. And of course, casting. One of the things that we're finding, the casting is sort of like a slow, rapid prototyping. But what we found is, this is a low temperature alloy, zinc, that we've cut things with a robot to produce different forms and then cast them. And trying to, again, give the ability for the designer to create a surface. Another challenge, Howard Elkus wanted to look like the Iguazu Falls, and so we're making the surface, taking and finishing it in such a way that it reflects light to make it look like water flowing, and doing different experiments with that. Or hammering and shaping the metal surface so that you develop textures that reflect light differently. In other words, try and open up the palette of surfacing in metal as broad as we can, not saying that you can do it one particular way, but to give you the tools to be able to do it in an infinite number of ways. This one, we took a zinc plate and milled it out. We call this a sort of a water pattern. And then we took this zinc plate and we pressed stainless steel into it. And this is a blue stainless steel to create this sort of a texture. Did it for an architect's house in Washington, D.C. But to get this tonal effect, rather than flat, but make it look like it's water. The way light hits it. The most amazing thing, I don't have the pictures here, but when you see it with perforations, it gives this almost depth effect. We experiment with glass, where we are casting glass with metal. And we found different metals work better. This is copper. The far side's the back side. This is the front side. And we found that ways that we could capture the red, intense red color. Now, this is a slow process, but the red tone's quite remarkable. Here, then, we've taken and slumped it. We've taken 7 layers of glass, 6 layers of copper, layered them up, and these images don't really show you, but by taking that, you can get this really interesting depth effect with slumped glass fused with metal. So the thing is relatively thick, relatively heavy, but the effect was quite amazing. Here's where we just simply took copper wool of a different alloy and slumped it between 2 pieces of glass. Kind of came out like again, the picture doesn't show the color that comes out of this and the depth of the color. But glass is kind of an experiment that we've got 4 kilns, and we're trying to look at ways of incorporating glass in with the metal fabrications or the metal opportunities that we offer the design community. Even trying to make, back to the holes, we like making the holes move. And this was working with Chuck Hoberman. We call it Tessellate. And these are ideas. This is SUNY. We put these panels up at SUNY. But the idea was, how do we make metal move in such a way? Now, where I think the need is to get with the design community and look at making this almost more organic in nature rather than very, very rigid geometries, although they look nice as well. But I think the more we can make it look like more organic move might be kind of intriguing as well. It's a very simple aspect of shaping. And you can control this with actuators hooked to a computer that shades the building when the sun moves around, or you make it move. But by changing the patterns, you can get all sorts of variations on the theme. But I was working with Chuck on a project in Saudi Arabia that we wanted it to look more like waves rather than a geometric form. But sort of like crystals growing. Project with Tom Main, that was an interesting one at Gates Hall and Cornell. Using simple perforated screens, stainless, but making it, laying it out on computer to produce these shading for the building. But it was, we just established a knife plate coming out from the curtain wall, and then bolted on these galvanized frames. So everything was made in the plant in Kansas City, goes out and just bolts on, and you're able to create this beautiful texture across the surface. Emerson was similar, using it as this texturing effect across the Emerson University here in LA. But it almost looks like birds, a flock of birds, but it served two purposes, shading the space and then protecting the rails. And this is another one of Tom Main's, this was in the Bloomberg Center in Roosevelt Island. And here is where we, using our image wall, we took an image across the surface, translated it to the movement of a robotic system. We cut all these with a laser and painted material. So they're laser cut off the preset program. And we had a couple of our interns working with one of my engineers. And repositioning one of our robots. So we rapid prototyped the device that hooks on the end of the robot. So we wanted to, it has to hit and bend the thing at a certain point, but it's all preset off the computer layouts. We want it to go a little faster. But you just simply have the bias predicted and then tell it where it has to hit the piece. So we're working on, this was actually one of your students back here. She's working with us, this was taken yesterday. So we repositioned the robot again. We wanted to figure out, okay, how do we get it to help weld these plates onto a curved pipe form. So there she is. And she programmed the robot to assist in the placement around this. And it was merely a test to see if we could do it on a more predictive fashion. And it made the parts with rapid prototype to test it out, and then set them on the pipe as they move across the bias. And we'd probably end up adding a second robot to weld it, but we used a human. But it's simply to research, can we translate that to some work we have coming up and make it more effective for us? You look at some of that and you go, well, you can also do other ways of creating that quicker where the human does it, but we want to reposition these things. This was a Lisa Iametto project using textures again on a parking garage down in Miami. In her form, she wanted to have various colors across the surface, and as it goes around the curve, there were these shapes all changed. We ended up having, 6 different or 5 different openings, but there are 40 types as they biased around. There were straight and curved, talls and shorts, lefts and rights, and a color scheme. So we had to create a map process so that we could, one, interpret how we're going to fabricate it, ship it, and then build it. And then Lisa she said, I don't want to see the structure. We got to come up with a way of not seeing the structure through the piece. So we analyzed 4 different structural possibilities. And we ended up choosing this one because it gave us the ability to do these more rapidly, more the same. And it was simply a tube with a fin welded onto it. And one went upwards, one went down. And here's how we modeled it, how the pieces would go so it wouldn't be seen through the opening. Every panel's a little different form, and we worked with Lisa on getting the edge so that the bend was just enough to show the difference in color. And here it's up. You can see the support pieces. And all these, each one was painted its own color, but by putting it together with the angle, created this mosaic across there. It was almost like origami. Oop. And the finished project is beautiful. Now, Miami's kind of going crazy on their garages. We've done another one at the other end of this with Leon. In this case, we used a gold physical vapor deposition stainless steel. And Chris and Ellen wanted these pieces cut, so we cut them and popped out. So we cut these with the laser, we V-cut the back, shipped them in the flat so we could fold them in the field. And I didn't realize it, but there's actually an angle that pigeons they fall off, can't nest. I had no idea. Now on PVD, or physical vapor deposit stainless, it's like titanium nitride on the one side, so it's golden. The back side's natural stainless, which actually worked out really well for this project because the way they light it. So at daytime, it looks this brilliant golden tones, different shadowing effect, and this wild texture across the surface. And then at night, takes on this whole different character as the stainless steel is reflecting the light on the inside. Here's some more, I just threw in some of these other garages that we're doing in Miami, and it's more applique on the surface. I think they're trying to scare the graffiti artists, but this is a museum garage, and it had all these great forms on them. And the one thing it doesn't show, and it kind of does in this picture, you kind of see a pink glow. Those panels are painted white on one side, pink on the other, and it has this really great effect. When it's lit, it just kind of glows this odd color. And then these big sections that we attached onto the surface. Here's looking from the garage out. We even hung fake cars on parts of it. And then these pieces, again, to, I guess, scare the graffiti guys away. But they just are, we've done like 8 garages down in Miami. The Miami Design District requires all garages to be art. This one's one we're doing right now, and it's actually pretty wild. You can't really see it, but these fins come off from it. This was the Paradise Plaza, another garage, but they had incorporated retail into it. It was definitely the more complex to do because the painted forms, the flat pieces coming together. Some last ones here. This is where we're working on Wiley Theater with Rex, Cool House. They wanted the Wiley Theater down in Texas made of, there were 7 types of extrusion forms that all went together. So imagine this is 110 feet in length. We hung it at the top and allow all the thermal movement to go downward. And here are the pieces to develop this beautiful texture across the surface. Tight little building in Dallas, Texas. We get into working with designers and other things. This is Jonathan Olivari and a group we started called UFP. This is in the VA. And it's what we call it as the aluminum bench. Oop, get this going again. And the idea is to have simply, it's 3 parts. It's the cast aluminum legs, the top, and the rails. The ends would be the 4th. But how do we keep the design to you? So we created the concept of shaping it on the internet, and you actually, as you do the shaping, you get the price of the piece. It adds where we need more, and then it goes immediately to the factory floor, on the parts that we need. We've done a number of these, and we're looking at other things to move into. Planters, things that have a parametric relationship. So if the relationship both in the structure and the fabrication and the cost. Here's our building latest engineering space, or our design space. It's influenced off of Frank Gehry's or O'Keeffe. I love the pods. And so, so we have to have some pods. So this is covered in zinc. And the idea was, if you look at the shingle here, it's not a rectilinear form. And to make it wrap around these different forms, if we cut it differently, you could use 10 different shingles and flip them around, and you get this mosaic across the surface that essentially has no rules. Here's the inside of the space. We wanted to accentuate the form and the structure so that when you walk in there, you feel, something's happening. The great thing too from architecture, I think, is the young people, when we're in the design phase of this, my engineers were looking at this and they said, well, get rid of that wall, make it glass. We want to be able to look at the factory floor. On the other side of the floor is where we have the more advanced manufacturing part. It's that connectivity to what's being made, just like you all want to be able to be involved with the fabrication and assembly of the parts. This is just the inside of one of the office or the meeting spaces. So, we have fun working even on our own building. We want to excite our people that come to see us and the people that work in the spaces. But I really appreciate the opportunity to tell you a little bit about what we do and hopefully get the chance to work with you in the future on different things. And thank you for the time.